All right, this is page 17 of the packet. Students will be able to construct a Maclaurin polynomial by using substitution and multiplication. That's kind of the goal today. Taylor series centered x equals c is f of c, f prime of c times x minus c, second derivative over 2 factorial, x minus c squared, and then the nth derivative over n factorial times x minus c to the n. And someone commented that I usually put n factorial over here, but it doesn't matter. It doesn't matter where it is. It's in the denominator. So the fact that they write it a little different than what I do, no big deal. If c equals 0, the series is called the Maclaurin series. So for centering at 0, it's called Maclaurin. Find the Taylor series for this function centered at c equals 2. Find the first 4 non-zero terms in the general term. So let's go f of centering at 2 is equal to, it's e to the 5x, so e to the 10th. And then the first derivative is 5e to the 5x. That's 5e to the 10th. Second derivative is 25e to the 5x. That's 25e to the 10th. First for non-zero. Now this is the last one then. 125e to the 5x, which is 125e to the 10th. Already lagging on me. Let's go. P sub n of x is equal to, find the first 4 non-zero. We got e to the 10th, 5e to the 10th times x minus 2. 25e to the 10th, x minus 2 squared over 2 factorial. And then plus 125e to the 10th, x minus 2 to the 3rd over 3 factorial. And the general term, we could write this with or without sigma notation. How about we write it with? If we start at 0, because I have, this is really over 0 factorial over 1 factorial, that this is going to be e to the 10th. Everybody has an e to the 10th. 5 to the n, x minus 2 to the n over n factorial. So we build the polynomial. There are 3 special Maclaurin series you must know. These are the series for e to the x, sine of x, and cosine of x. So e to the x is 1 plus x squared over 2 factorial, x to the 3rd over 3 factorial, plus keep on going. So that's x to the n over n factorial. Each derivative of e to the x is e to the x, and all e to the zeros are 1. So all those coefficients are 1. Cosine is an even function, symmetric over the y-axis. So this is going to be, oh, not sine, it's cosine. Cosine of x is even. 1 minus x squared over 2 factorial. X to the 4th over 4 factorial. X to the 6th over 6 factorial. This computer is on its last leg. Let's go negative 1 to the n if I start with 0. X to the 2n over 2n factorial. Sine is odd. So sine is equal to, or approximately equal to, I need odd powers. X minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial, x to the 7th over 7 factorial. So that's going to be negative 1. Should we start with 1? Why not? To the 2n minus 1, x to the 2n. I don't need 2n minus 1. I just need n plus 1. 2n minus 1 over 2n minus 1 factorial. We can manipulate these three special series or any series we are given to find the other series by using the following techniques. Substitution, multiply or divide the series by a constant and or a variable, add or subtract two series together, differentiate or integrate a series. So we get term by term derivative or term by term antiderivative. Integration. Find the Maclaurin series for f of x equals sine of x squared. Let's start out with sine of x. That's, we just did that. X minus x to the third over 3 factorial. X to the fifth over 5 factorial. X to the seventh over 7 factorial. Then now, sine of x squared is equal to, we're going to replace all the x's with x squared. So x becomes x squared. If we replace x with x squared and x to the third, that's x to the sixth. Plus x to the 10th over 5 factorial, and then x to the 14th over 7 factorial. Well, if we're going to write the general term, we notice that the powers are increasing by 4, and this is linear, with the slope being 4. So negative 1 to the n plus 1. I think I'm going to start with 1. And the only reason I'm starting with 1 is because this is 1 factorial. If that was 0 factorial, I think I'd start with 0. But you can start with anything you want. All right, x to the, they're increasing by 4. But now if I plug a 1 in there, it's 4. And I need that first one to be a 2. So minus 2. Over 2n minus 1 factorial. All those are odd in the denominator. So we turn sine of x squared into a polynomial. That's the whole goal of this. Turn it into a polynomial. On this one, let's start out with cosine. Cosine is even. So 1 minus x squared over 2 factorial. X to the fourth over 4 factorial. X to the sixth over 6 factorial. Remembering that this alternates. Unable to create a temporary folder. Okay. X cosine of x is equal to, now we're distributing x through this. X to the third, x to the fifth, x to the seventh. So that's going to be, should I start with, this is over really in the pattern 0 factorial. So I think I'll start with 0. Negative 1 to the n. X to the, these are just odd, or in other words, we're adding 2 every time. That's the slope of that line. But if I plug 0 in, that'll be 0. So plus 1 over 2n factorial. Questions on these, on building the polynomials. Substitution and multiplication is what I did on these two. Find a Maclaurin series for e to the 2x. A Maclaurin, all right, well, e to the x is 1 plus x squared over 2 factorial, x to the third over 3 factorial. Keep on going. E to the 2x is a replacement. We're replacing x with 2x. So 1 plus 2x plus 4x squared over 2 factorial plus 8x to the third over 3 factorial. Keep on going in that pattern. Well, you can, I mean, should we write this? Let's see if I wrote this in sigma notation or not. Oh, where is this? Oh, I did. So n equals, this is over 0 factorial. We just don't write these. Over 1 factorial. So how about starting with 0 to infinity? And we have not alternating. So 2 to the n. We got x to the n over n factorial. I could have written that as 2x to the n. Use your answer to A to find a Maclaurin series for the function, given that function h, given that h prime is this. So we're going from h prime back to h. So we want to integrate both sides. So we're integrating this. So we're going to do term by term integration. So h of x is equal to, well, notice that we're writing these polynomials backwards, by the way. If you wrote a quadratic, you would write it like this: x squared plus 2x minus 3. That's how you'd write it. And then when you'd integrate, at the end, you'd put plus c. But we're going to put c at the beginning here because we're writing these backwards. So this is the plus c. Antiderivative of 1 is x. Antiderivative of 2x is x squared. Antiderivative of this one would be, 4/3. It's already lagging on me. X to the third over 2 factorial. And then plus 8 over 4. X to the fourth over 3 factorial. Keep on going. Now they say that h of 0 is 3. So 3 is equal to c plus 0 plus 0. All of these are going to have an x in it. All of those end up being 0. So c is equal to 3. So h of x is equal to 3 plus x squared plus 4x to the third over, if you want to get really clever, it's over 3 factorial plus 8x to the fourth over 4 factorial. Keep on going, because 2 factorial times 3 is 3 factorial. Now the sigma notation is a little weird in that the pattern doesn't really start until we get to this one right here. There's where the pattern starts. So it's legal in Nebraska to write this: 3 plus x squared. And then plus, all right, this is where the pattern starts. So we're going to say n equals, I don't know, how about 3? 3 to infinity of, we would go 4 to the n, oh, not 4, because it's 2 squared and 2 to the third. So how about 2 to the n minus 1, x to the n over n factorial. There we go. I like this one because it shows that, well, you write the sigma where the pattern actually starts, and you can just add on the others. That's okay to do that. It doesn't seem right, but it's fine. No problem. Construct the fifth order Taylor polynomial in the Taylor series for the function at x equals 0. Use the polynomial to estimate f of 0.1. So f of x, well, no, where are we centering this? At 0. It's a Maclaurin. So f of 0 is equal to e to the 1 minus 0, which is just e. F prime of 0, let's write the polynomial first. Let's go, or not polynomial, but the function derivative first. It would be e to the 1 minus x, but the derivative of negative x is negative 1. This is negative e to the first. Second derivative would be e to the 1 minus x, because you'll take a negative times a negative. And now I kind of see the pattern that it's alternating between positive e and negative e. Fifth order Taylor polynomial. Well, that's going to be negative e. That'll be e, negative e. Centered at 0. So p sub 5 of x is e minus ex squared over 2 factorial, ex to the third over 3 factorial, and we're going to keep going. Alternate. Minus, plus, minus, plus. That needs to be a minus. Plus. And minus. Use the polynomial to estimate f of 0.1. So I can pop up. There we go. Drag. Clear that. So p sub 5 of 0.1. Let's see how good of an approximation this is. There is an e button. It's the second function of divide. So second e minus e times 0.1. Yeah, minus plus e 0.1 squared minus e 0.1 to the third divided by, oh wait, did I miss that? Divide by 2? Yeah, I did. This is the exciting part of notes, watching me do this. Divide by 6 plus e 0.1 to the fourth divided by 24. And finally minus e 0.1 to the fifth divided by 120. See how we did. 2.45, keep going. 2.459603107. And f of 0.1 is equal to e to the 1 minus 0.1 is 0.9. Not bad, right? 2.459603111. So if we subtract these two, get an error at about, what, 8, 9 decimal places? Error is equal to 4.157 times 10 to the negative 9. Pretty accurate. And, you know, when you do this on the test or a quiz, a pretty good indication that I probably did this right if I'm getting an accuracy of 9 decimal places. Find the Maclaurin series for f of x. Give the first 4 non-zero terms and the general term for each series. Let's go. E to the x is 1 plus x squared over 2 factorial, x to the third over 3 factorial. All the derivatives are e to the x. E to the 0 is 1. All the coefficients are 1. So 2x e to the x is, we're multiplying. So we're distributing. 2x squared, 2x to the third, 2x to the fourth. Well, they all have a 2. How about we start with 0? X to the n plus 1 over n factorial. And that makes sense because there's one more x now. N plus 1. On this one, let's start out with cosine. Cosine of x. That's an even function. So we have the even powers. 1 minus x squared over 2 factorial. X to the fourth over 4 factorial. X to the sixth over 6 factorial. Always replace first. So now we're going to replace x with 2x. So 1 minus 4x squared plus 16x squared to the fourth minus, 8 and 8? 64. And now we're going to multiply all that by x. And we're going to do it real slow because my computer is lagging. plus 16x to the 5th over 4 factorial. 64x to the 7th over 6 factorial. Oh, we got 2. If I start with 0, that'd be 2 to the 0. But we're increasing by, oh, did I mess this up? No, 1, 3, 5, 7. Oh, I'm doing the 2s. 2, 2 squared, 2 to the 4th, 2 to the 0, 2 squared, 2 to the 4th. What? What am I missing here? Oh, no, these are 4. 4 to the 0, 4 to the 1, 4 to the 2, 4 to the 3. Okay, yeah, not 2s. That's what I'm, yeah. 4 to the, oh, it's alternating. Negative 1 to the n if I start with 0. 4 to the n. 1, 2, 3, yep. X to the 2n plus 1 over 2n factorial. Finally got it. I was trying to make them 2s and then it wasn't working. Construct the series for sine of x squared. Sine of x is odd, so x minus x to the 3rd, x to the 5th, x to the 7th. Sine of x squared then is x squared, x to the 6th, x to the 10th, x to the 14th. That's a 2. So this is going to be, if we start with, this is over 1 factorial. Maybe we start with 1. Negative 1 to the n plus 1. X to the 2, 6, 10, 14. Adding 4. So 4n, but if I plug a 1 in, that'll be 4. Minus 2 over 2n. What am I start with? 1 minus 1 factorial. Questions on any of that? All right. Construct the series for 1 over 1 minus x to the 3rd. Well, there's a couple ways to do this. If we're going to tie it to what we're doing today, this is how I would tie it in. I'd start with 1 over 1 minus x. That's the power series, where a sub 1 is 1 and your r is x. So plus x, x squared, x to the 3rd, keep on going. Then we can replace all the x's with x to the 3rd. So 1 over 1 minus x to the 3rd is 1 plus x to the 3rd, x to the 6th, x to the 9th, keep on going. So that's just going to be x to the 3n. Like I said, that's tying it into what we're doing today. It's a substitution. Substitute x to the 3rd in for x. But if you just at the beginning, you recognize it's geometric and make r x to the 3rd, you get the same thing. 1 plus x to the 3rd, x to the 6th, x to the 9th, keep on going. Find the Maclaurin series for f of x. Use the first 5 non-zero terms to estimate f of 0.2. Round to 10 decimal places. We're going to try to find the polynomial for this by doing substitution and then multiplying. How come that won't right? There we go. Hint, start with the natural log of 1 minus x. Find derivatives and build the polynomial from there. Ready, set, go. Does it make any sense at all? That's what we're going to find out. So we're going to start out with f of x is natural log of 1 minus x. And where are we centering this? Probably at 0. Find the Maclaurin. Yeah, Maclaurin. There we go. Natural log of 1 is equal to 0. Then f prime of x is 1 over 1 minus x. Or how about we do it like this? 1 minus x to the negative 1. But if we plug 0 in there, we just get 1. Second derivative is negative. Oh, wait. Oh, I messed up. Anybody catch it? It's negative. Times a negative 1. That's negative. So that's negative 1. Forgot the chain rule. So now when we multiply negative 1 times a negative, that's a positive. So it's really 1 minus x to the negative 2, but then times negative 1. So all of these are going to end up being negative. So this is also negative 1. This is going to be, it's really negative 2 times a negative 1 is 2. 1 minus x to the negative 3 times negative 1, so it's negative 2. Because 1 minus 0 is 1. 1 to the third is 1 in the denominator. So to the fourth is 6. 1 minus x to the negative 4 times negative 1. So that's going to be 6. Use the first 5 non-zero. 1, 2, 3, 4. Here's the fifth non-zero, which ends up being 24. 1 minus x to the negative 5 times negative 1. That's 24. Well, those are the factorials, right? So this is the constant to the x squared, x to the third, x to the fourth. This is your x to the fifth. So first of all, let's go with natural log of 1 minus x is negative x minus x squared minus x to the third over 3 factorial, but the 2 cancels out the 1 and the 2 in the factorial, so it just ends up being 3. Oh, I forgot the negatives on this one. Negative 6, negative 24. Minus 6x to the fourth over 4 minus 20. Oh, no. They cancel. I'm canceling. That's x to the fourth over 4 minus 24 over 5 factorial is just 5. So x to the fifth over 5. Now we're going to go natural log of 1 minus x squared. So negative x squared minus x to the fourth, x to the sixth, x to the eighth, x to the 10th. And the last part is multiplying all that by x. Negative x to the third, x to the fifth, x to the seventh, x to the ninth, x to the 11th. All right, now if we're going to approximate 0.2, so we're going to evaluate this when x equals, oh, is it? No, not 0.2. Oh, it is 0.2. 0.2. Lagging. All right, tedious, right? Negative 0.2 to the third minus 0.2 to the fifth. Oh, it's all minus. Minus 0.2 to the seventh divided by 3 minus 0.2 to the ninth divided by 4 minus 0.2 to the 11th divided by 5. See how we did. Negative 0.00, really lagging, 8, 3, 2, 4, 3, 9, 8, 8. So what is 0.2 times natural log of 1 minus 0.2 squared minus, I made a mistake somewhere. Anybody catch it? Oh, let me see. I have this. X squared over, oh yeah, over 2. So that was it right there. How'd I lose that? I lost it. Oh, I lost it way back here. Okay, all right. Well, that should be an easy fix. Yeah, thank you. That's got to be it. 5 by 2. It's that answer right there. 0.2 natural log of 1 minus 0.2 squared minus, oh, that's much better. There we go. There we go. It was that divide 2. I lost the 2. All right. Any questions on this? Tedious, for sure.